Well, welcome everybody to EPA's monthly webinar series for small systems. Today's topic is alternate disinfection, dichlor and trichlor. A little bit of housekeeping before we start. The bottom of the slide is the webinar support phone number if you're having webinar problems. Also, the recordings of this webinar will be found on the website that's on the very bottom of the page. Sorry about that. Very bottom of the page. You can find it there. And also, we are very glad to offer a certificate for one continuing education contact hour for viewing this webinar. The requirements for getting the certificate are that you must be registered for the live webinar or be in a room with someone who's registered. You must attend for all 60 minutes. If you are in a room with others, the names of the people not logged in must be provided by the person who is, and send the names to that address there. If you didn't request the credit registration, you can still sign up and send an email request to that the same address there, or respond to your registration confirmation email. One note is that the certificates of completion cannot be provided for viewing the webinar recordings, just this live webinar. So with that, we would like to know how to improve our webinar series. So if there's any topics that you would like us to cover, let us know. Or if you know of any communities that could be possible case studies, or any other comments, please send it to us. And you can do that by taking the Survey Monkey, which is the address down at the bottom of this screen. So we'd really like your anonymous survey about our webinar. It helps justify the webinar series, and also we're always looking for topics that are of interest to the drinking water community. So please take that Survey Monkey. So a little bit of other housekeeping. If you're interested in downloading the slides for today's talk, you can find them in the handout box that's in your little pop-up window, dialog window on your screen. Also, if you have questions for the speakers, feel free to do them during the talk and put them in the questions box. That would help us organize the questions at the end of both speakers. We'll handle all the questions all together. So, and finally, if you missed the poll question and you have more than one person in your room, please type that number into the question box. It'll help us document how many people attend the webinar. Again, it helps us justify the webinar series. If you have any other questions or comments, feel free to throw them in there. We'd love to hear about anything you might have interest in. Okay, so our first speaker is David Wammen. Dave is a research engineer with the EPA's Office of Research and Development in Cincinnati, Ohio. He's a registered professional engineer with over 20 years of experience. He received his BS from Rose-Hulman Institute of Technology and his master's and PhD from the University of Texas at Austin. Dave's drinking water research areas include biological treatment, distribution system nitrification, and disinfectant chemistry. And with that, I'll pass it off to Dave for his presentation.
Okay, thank you, Tom. So today I'm going to talk a little bit about dichlor and trichlor. And I have about 4 things I want to get across today. The first is I want you to be familiar with chlorinated cyanurates and their use. Second, I want you to understand their water chemistry and the associated implications. Third, I'll go over a few things to think about in terms of how they are used in practice. And finally, I want to make you aware of a web-based application that will actually allow you to simulate the water chemistry in these systems, and about some future updates that are planned to the application. So to start, these first couple slides actually refer to outdoor pools, but I think it's important to understand why and how chlorinated cyanurates were originally used. So as we know, free chlorine consists of hypochlorous acid and hypochlorite ion. One thing about it is it can decompose in sunlight because it absorbs UV light. So this is a problem in outdoor pools, as hypochlorite ion absorbs at wavelengths that reach the Earth's surface, which leads to chlorine residual loss. And as a result, studies have shown that free chlorine only, if it's only present in outdoor pools, has an approximate half-life of only about 30 minutes, meaning it will basically degrade by half in 30 minutes under typical sunlight conditions. So to address this free chlorine loss in outdoor pools from sunlight exposure, what has typically been done is cyanuric acid has been added to form these chlorinated cyanurates. First, cyanuric acid is not related to cyanide, as the name might suggest, but it has been used in outdoor pools since about 1958 to stabilize free chlorine by forming these chlorinated cyanurates, which actually lowers the standing free chlorine concentration because of some of the free chlorine becomes bound up in these chlorinated cyanurates. So the chlorinated cyanurates basically serve as a reservoir of free chlorine, such that the free chlorine can be released back into the water if chlorine demand occurs. Importantly, chlorinated cyanurates absorb at wavelengths lower than those that reach the Earth's surface, which is why they're able to stabilize the free chlorine in outdoor pools. And just as a reference point about how much chemicals are typically added to outdoor pools, typically recommendations are between 2 and 4 milligrams per liter of total chlorine, and then 30 to 50 milligrams per liter of cyanuric acid is common. And so just to highlight what I was talking about, this graph shows the stability of 2.5 milligrams per liter of total chlorine exposed to sunlight with varying doses of cyanuric acid. So the y-axis is the percent of total chlorine remaining, and the x-axis is time in hours. And this first line just shows adding free chlorine only with no cyanuric acid addition and how it essentially goes away over time. And again, it goes about half of it's gone in 30 minutes, and then about 3 hours, not much is left. But if you add some cyanuric acid, so initially 25 milligrams per liter, you can see that the stability greatly improves over time. And if you add some more cyanuric acid, its stability improves further. So the take home here is that cyanuric acid improves chlorine stability in outdoor pools by forming chlorinated cyanurates. So now I want to start moving towards talking about drinking water. So here is cyanuric acid's chemical structure. It actually comes in 2 forms, but that really doesn't matter for what we're talking about today. But what does matter is where these boxes I've just popped up correspond, and that's because these 3 hydrogens, these spots can either have hydrogen in there, they can be empty, which means they'll have a negative charge, or they can actually be occupied by chlorine. And so also this base structure without the 3 hydrogens is the cyanurate structure, and it's shorthanded by CY. So cyanuric acid's chemical formula can be represented by H3CY. So if you add cyanuric acid to water, there are 4 possible chemical species that I'm showing can form here, and this basically depends on pH, whereas if you increase pH, you move to the right, it's an acid, it drops hydrogens as you increase pH. If you would then add some free chlorine to the water, then you can form these chlorinated cyanurates, and there's 6 of them, which I'm showing here. And so, and in lieu of adding free chlorine and cyanuric acid separately, what you can also add specific chlorinated cyanuric chemicals, which are typically referred to dichlor and trichlor, which is what I'm highlighting now. So adding either dichlor or trichlor is effectively adding both free chlorine and cyanuric acid in a defined ratio, and I'll explain a little bit more on this in the future. But overall, the bottom line here is in a system where you have free chlorine and cyanuric acid present, no matter if you add them as dichlor or trichlor or free chlorine and cyanuric acid separately, this equilibrium occurs where all these species can be present. There's actually 10 chemical species associated with cyanuric, and there's 12 equilibrium equations, of which 9 are independent, that define this equilibrium. So the take home here is there's this equilibrium between cyanurate, free chlorine, and these chlorinated cyanurates. And also to keep in mind, and we'll get to this a little later as well, that free chlorine is actually the real disinfectant in these systems, and these chlorinated cyanurates are not really considered disinfectants in and of themselves. So I just want to briefly summarize some terminology at this point. So again, free chlorine, when I mention free chlorine, we're talking about hypochlorous acid and hypochlorite ion. Available chlorine is the 6 chlorinated cyanurates, and they're called available because they're available to release free chlorine back into the water. Total chlorine is then the sum of the free chlorine plus the available chlorine in these systems. And total cyanurate is the sum of the 10 species with CY, or the cyanurate molecule. So now specifically with respect to drinking water, use of dichlor and trichlor was first approved in 2001 under FIFRA for the routine treatment of drinking water. Just to give you an example, here's an example I provided in your notes of a dichlor label that you might find on the product, and it just tells you to basically add it until you get 0.2 milligrams per liter throughout the distribution system. And if you saw a trichlor label, it's basically the same label, except for you're adding 1 ounce to 9,000 gallons now versus 1 ounce to 6,000 gallons because trichlor has more chlorine in it. In addition to the FIFRA registration, manufacturers have obtained NSF 60 certification for adding dichlor or trichlor to drinking water. This comes with a 30 milligram per liter maximum concentration by how it's approved under NSF 60. 6 dichlor and 7 dichlor manufacturers have received certifications for products, and they might have multiple products. But nobody has ever gotten certification for cyanuric acid proper for drinking water, even though they use it in the pool industry. Typically find only dichlor and trichlor is how you add cyanurate in drinking water. WHO, World Health Organization, also has some guidelines shown here. But practically, when you're talking about drinking water, your total cyanurate concentration that you're actually going to see in drinking water is only about 5 to 10 milligrams per liter, and that would be on the maximum end of things. As you remember from that earlier slide, pools can have up to about 100 milligrams per liter in their waters. So we're an order of magnitude lower in terms of cyanurate in drinking water, just to keep that in mind. And the bottom line here is that states, tribes, or territories may approve the use of dichlor or trichlor. One other thing I want to point out is that it can be confusing how FIFRA and the Safe Drinking Water Act are related as for disinfectants. Therefore, I want to make you aware of a new quick guide that was developed to help explain how these two regulations are related. This was actually released in September 27, and it can be accessed at the link provided on this slide. So if you have a chance, take a look at that if you have some more questions. So in drinking water, as I mentioned, we don't add cyanuric acid proper to free chlorine. Rather, we add dichlor or trichlor added. So here are the chemical structures of dichlor and trichlor. I just want to point out that dichlor actually is sold in two salt forms. The first here I'm showing is anhydrous. There's also a dihydrate form, which just adds 2 waters. That's what dihydrate means, is 2 waters. So you just have a couple waters on there. And then on this table here, I've summarized in your notes some properties of the free chemical. So it lists the percent available chlorine, which ranges from 52 to 92%. As you would expect, trichlor has an additional chlorine on its structure, therefore it has a higher percent chlorine. Concentration solutions of dichlor have a relatively neutral pH, while solutions made up of trichlor are actually acidic. Because dichlor is a salt, it is more soluble than trichlor and dissolves faster in water. And then finally, I've provided you the total chlorine and total cyanurate that you get if you actually make up the chemicals by the doses given on their FIFRA labels, which is 1 ounce to 6,000 gallons or 1 ounce to 9,000 gallons, just kind of as reference for your notes. And then another reference for your notes, if you go back at these slides, is just a table here that summarizes various concentrations that may be helpful when dealing with dichlor and trichlor. Basically, it provides ratios for various ways of thinking about adding the chemicals to the water. So the first 2 rows provide how much total chlorine or total cyanurate you're going to add per milligram of chemical added. And then the last 2 rows provide how much chemical or total cyanurate are added per milligram of total chlorine added. And again, specifically note in the last row here that if you're trying to add the same amount of total chlorine to the water, you effectively add 50% more total cyanurate with dichlor versus trichlor. So one question might be, why would we even use these chemicals in drinking water? Because in drinking water, we're not likely going to be exposing the waters to sunlight, so the reasons they're used in outdoor pools are not necessarily why we would use them in drinking water. And here are some of the stated benefits by the manufacturers. Basically, they're sold as solid chlorine sources and are promoted as safer than liquid and gas forms of chlorine. And the solids have much longer storage lives, so on the order of years. They're concentrated forms of chlorine, as I showed you on the previous slides. A couple other benefits specifically for dichlor over trichlor is that I mentioned before that it dissolves much easier in water. It's much more soluble than trichlor. And again, it produces a solution around a neutral pH versus acidic. There are a couple other things about these chemicals that might be relevant in that, based on their known chemistry, and we'll get into this in a little bit, they may provide a greater residual stability and maybe delay or produce lower regulated DBP formation than using free chlorine alone. And so that kind of breaks down the first part of my talk here. Just to provide some background, the major points I summarized here that dichlor and trichlor are the chemicals that are added to drinking water, and they effectively contain both free chlorine and cyanurate. They are chlorine sources that they've been FIFRA approved. They can be NSF 60 certified. And overall, you can view that there exists a very fast equilibrium between free chlorine and these chlorinated cyanurates. So if there's anything disturbance in the system, like free chlorine is used up, it's going to re-equilibrate very quickly and release more free chlorine into the water. So the next part of the talk is going to be getting in a little bit more on the water chemistry. The one issue I want to make you aware of, I want you to keep in mind as you're thinking about this water chemistry, is that with dichlor and trichlor, I'll discuss this shortly in greater detail, you can't accurately measure the standing free chlorine in these systems with currently approved methods, and that's a major issue. So what happens is you end up measuring the total chlorine, which is the free chlorine plus the chlorine that's actually bound in the chlorinated cyanurates, meaning you're going to bias your measurements high. As far as the water chemistry, the water chemistry model was basically developed in 1972 and for 25 degrees Celsius by O'Brien. And what this boils down to for these systems is you need to know three things to be able to simulate the water chemistry. You need to know how much total chlorine is in the water, you need to know how much total cyanurates in the water, and you need to know the pH of the water. If you know these three pieces of information, then you're kind of left with 12 unknown chemical species and 12 equations, which really not the details aren't here, isn't that important. What's important is you have the number of unknowns equals the number of equations, so we can solve this water chemistry problem and determine the concentration of any of these species. And what we're concerned with is understanding the free chlorine in these systems. So getting into that, in these systems, there's various things that can impact the amount of free chlorine actually present at a given time. So this graph here shows the free chlorine percent of the total chlorine versus pH. Remember that the balance of the total chlorine that isn't free chlorine is in these chlorinated cyanurates. So if you make up a 1 milligram per liter total chlorine solution with trichlor, its percent free chlorine is shown here versus pH. And you can see the variability in the percent free chlorine versus pH, where you have a minimum occurring around pH 7 to 7.5, and you have very little impact on chlorinated cyanurates at pH is above 9, where basically all the chlorine is present as free chlorine at the higher pHs. The dot on here shows the actual free chlorine concentration at pH 7. So as I said, it's a 1 milligram per liter solution. 72% is that is free chlorine, so that's a 0.72 milligrams per liter of free chlorine. So the first take-home message with the chemistry is the percent free chlorine is going to vary with the pH. If you make a comparable solution up with dichlor, it looks like this. A dichlor produces a lower percent free chlorine than trichlor because you're effectively adding more total cyanurate for the same amount of total chlorine, leading to more of the chlorine tied up in the chlorinated cyanurates. So the second take-home message is that percent free chlorine is going to be lower with dichlor compared to trichlor for equivalent chlorine solution. Now, if you make up higher concentrations, the percent free chlorine is not constant and decreases substantially. So if you make up a 4 milligram per liter solution of dichlor versus a 1 milligram per liter solution, you've increased the total chlorine by 3 milligrams per liter, but your free chlorine's only gone up by 1 milligram per liter. So there's a diminishing returns here. So to increase dosage, the percent free chlorine is actually going to decrease. And then finally, the thing we have to deal with in real water is that we actually have chlorine demand. So we have to take that into consideration. The cyanurate that's in the water can be considered essentially conservative, and it's not going to go away over time, but the chlorine in the water can react away, and your total chlorine concentration can go down, while your total cyanurate concentration remains constant, and that's what I'm highlighting here in this last plot. So if that original 4 milligram per liter of dichlor was decreased to 0.2 milligrams per liter as chlorine of dichlor, you have a very small fraction of that that's present as free chlorine now. Only 0.03 milligrams per liter of that 0.2 milligrams per liter. So the fourth take-home message is that the percent free chlorine decreases with increased chlorine demand of the water. So next I want to discuss how chlorinated cyanurates may impact disinfection and residual stability, where we can just view residual stability as something that we can also relate to DBP formation. First, if you simplistically view disinfection as essentially hypochlorous acid reacting with an organism, how fast this is going to occur can be represented by the simple reaction rate I'm showing here. In this reaction rate, you'll have a constant multiplied by some HOCl and organism concentrations, and the bottom line here is the bigger that number, the faster things are happening. So the bigger this number, the faster things die. Likewise, you can view residual stability as a reaction of HOCl with total organic carbon. So in comparing a system with free chlorine only and a system that uses dichlor and trichlor that maintain the same total chlorine concentration, the only difference is really going to be the HOCl concentration. And so by adding dichlor and trichlor, as I showed you on the previous slide, you effectively decrease the free chlorine concentration, which is going to slow both of these reactions up here. So you would expect the disinfection to be slower in systems with dichlor and trichlor, and residual stability maybe to increase, which may then lead to slower DBP formation. So as opposed to outdoor pools where stability mainly comes from shielding free chlorine from sunlight, in drinking water, stability is going to come from having an effectively lower free chlorine concentration in the water. And so to illustrate these points, I want to show a few graphs. So first, here's the graph showing the log in activation versus time versus crypto. So basically here, the steeper line seems faster in activation. So this first line shows adding only free chlorine, and then these next lines are going to show that same free chlorine concentration, but now with increasing additions of cyanuric acid. And as you can see, as you increase the cyanuric acid that's added, the lines become flatter, meaning kill's happening slower. So the cyanuric acid addition slows down the inactivation. Here's another example for disinfection, and this time it's for streptococcus. So this graph is now showing the time for 99% kill versus concentrations. And shown here a variety of experiments at various total cyanurate concentrations. When plotted using total chlorine concentration, you see no relationship between concentration and kill. Now, what we expect to see here is as you increase concentration, the time to kill should go down, so we should see a line sloping to the right. And we don't see that if we plot against total chlorine concentration, but if we actually calculate the free chlorine or hypochlorous acid that's there, we then see this nice trend, which kind of shows that HOCl is actually the disinfectant in these systems, and that the chlorinated cyanurates are not important disinfectants relative to hypochlorous acid. So to illustrate the impact I mentioned on residual stability, here are actually some results we did in our lab for an experiment where we took a surface water, same surface water, and we either added 4 milligrams per liter of free chlorine, dichlor, or trichlor as total chlorine to the water. And this graph then just shows the free chlorine DPD measured chlorine concentration over a period of 42 days. And just to compare the residual stability, I've chosen to note how long it took to decrease from 4 to 0.2 milligrams per liter for each chemical on 2 different bases. And depending on this basis, your interpretation of whether you've really improved residual stability may vary. So if you go solely by the free chlorine DPD test, which as I mentioned previously measures actually the total chlorine in the water, then you see an advantage in using dichlor and trichlor over free chlorine where you've extended the residual stability for a significant amount of time. But if you actually calculate how much free chlorine is actually present in each of these points, and that's the second column represented by actual free chlorine, then trichlor and dichlor aren't really giving you an advantage. So if you're working on the grounds that you just want some residual there as far as detectable, then maybe dichlor and trichlor give you an advantage. But if you're actually trying to meet a numeric standard and want an actual numeric standard, then maybe free chlorine is still better than trichlor and dichlor in terms of residual stability. So that covers the second point I was trying to convey. The major points are that we know the water chemistry 25 degrees Celsius, therefore we can calculate the percent free chlorine, and it varies based on several factors. And that hypochlorous acid is the important disinfectant in these systems still. Now I want to move on to some things to consider about dichlor and trichlor. And the main thing I want to talk about is this issue of knowing the true free chlorine concentration in these systems that I mentioned earlier. The reason this is so difficult is that free chlorine is in this fast equilibrium with the chlorinated cyanurates. Therefore, if you have a method that reacts with free chlorine or changes pH, it's going to disturb this equilibrium. And specifically, if you have something that reacts with free chlorine, it's going to decrease your free chlorine concentration. Chlorinated cyanurates are going to very quickly release free chlorine back into the water. That's going to further react with your method, so you basically suck out all the total chlorine in your water. So knowing this, what doesn't work? So we know from the early research, actually in the 70s and 80s, that DPD and ampermetric titration-based free chlorine methods don't work. This is because both of these methods actually react with free chlorine and actually change the sample pH in the method. There are a couple of newer methods that I'm going to show you some results on that we did in our lab too, but they suffer the same limitations. Overall, I know of no approved method right now that can directly measure free chlorine in these systems under what would be considered drinking water conditions. So to highlight the bias we see with the free chlorine test, here I'm showing some results of some research we conducted where we compared several different methods. So the y-axis here shows the measured concentration from each method, and the x-axis shows the added total chlorine concentration in the sample. And this was done with dichlor pH 7. So the first bar in each of these bar sets is the free chlorine concentration that we want to be able to measure, because this is the simulated or the water chemistry known free chlorine concentration in these samples. While the remaining bars in each set are what we actually measured. And so we're comparing DPD colorimetric free and total chlorine done with a colorimeter and with a Hawk SL1000. And we're also showing the free chlorine indol phenol method on the colorimeter. And it's very easy to see here that all the methods are measuring total chlorine. And none of them are actually capturing the free chlorine for the reasons I mentioned before, and that they all react essentially with the free chlorine in the sample. We also did this with dichlor pH 9, trichlor pH 7 and 9. We received similar results. So free measures total chlorine. So we also looked at ampermetric titration just to verify what was seen in the literature. In this case, we made up various solutions of 2 milligrams per liter of total chlorine by some methods. Again, the y-axis is the measured concentration from the method, while the x-axis is various solutions we made up. The first bar in the set, again, is what we wanted the free chlorine measurement to show, while the other bars are what each method actually measured. So the first 5 bar sets, which is the CYA0 to CYA4, were made by adding various cyanuric acid concentrations to this 2 milligrams per liter of total chlorine. And you will see that even though the actual free chlorine concentration decreased with increasing cyanuric acid addition, the measurements remain the same for essentially both the ampermetric and the DPD free chlorine measurements. And just as a comparison, we also made up some dichlor and trichlor solutions. So again, free is measuring total chlorine in these systems. So that's what doesn't work. What could work in terms of measuring free chlorine? So the method, again, must not disturb the equilibrium, so you can't change the pH, and you need to provide a direct measurement of free chlorine without really reacting with it. The original work that they developed the water chemistry was actually based on just straight UV absorption or molar absorptivity, but those are in buffered DI water, essentially. So those aren't going to work in natural samples because of interferences and detection limit issues. There's also been some work using ampermetric electrodes, but what these have shown is that they measure somewhere between the free and total chlorine in the sample, meaning they measure a portion of the chlorinated cyanurates that are present. One option that we have pursued is that using the known water chemistry to estimate the free chlorine concentration. And this requires, as I mentioned before, that we know 3 things and also overcome some issues that we're trying to work through. So as I mentioned previously, we need to know the pH, total chlorine, and total cyanurate to use the water chemistry model. So in a water sample, we can get pH easy enough. We can directly measure that. We can actually get total chlorine as well, because we can use the fact that the free chlorine DPD method actually measures total chlorine. So we can use the interference to our advantage here, or the bias to our advantage. Measuring total cyanurate is the first issue. Most methods that measure total cyanurate are made for outdoor pools and are geared for much higher cyanurate concentrations, and their lower limit is kind of the upper limit of what we would see in drinking water, about 5 milligrams per liter. So if we need a better method to measure this down to drinking water concentrations of about 0.1 milligrams per liter of total cyanurate. But this could be worked around still by estimating total cyanurate from the known dosing of the chemical to the water and assume that it remains conservative in the water, which is a pretty good assumption. The other limitation to the water chemistry model is that it's only been studied at 25 C, and drinking water is at various temperatures. So we need a drinking water, we need to update to over the range of drinking water temperatures we might see. Therefore, we have to expand that model. And each of these equilibrium constants in the model is temperature dependent, so that's quite an endeavor to try to update 10 equilibrium constants. So there's a couple other things to consider, and I'm just going to kind of throw this slide up here for your notes. The main thing I want to highlight is this thing I talked about earlier, and this is the idea of what do you require for a residual, whether it's detectable versus a number. And your opinion of dichlor and trichlor may vary on what your conditions are that you're trying to meet. And so that kind of gets us through point 3. What the main points are that there's currently no approved method that will measure the true free chlorine concentration systems using dichlor and trichlor. We're able to simulate the free chlorine concentration at 25 C. And then what I want to do in the last couple minutes here is just make you aware of a web-based application I've developed to simulate the water chemistry and some ongoing research to expand it. So the application is located at the link shown on this slide. It was developed for 25 C using the O'Brien equilibrium model. And again, you got to know the total chlorine, total cyanurate, and pH range you want to simulate. And then you can get outputs that you can download or view that'll tell you the free chlorine in the sample. Just to make you aware, there's also a document going along with the application. The cover page is shown here, and it's available at the link. But still, a limitation with the current application is that the water chemistry is only valid for 25 C. So to get around this temperature and to try to make it reasonable experimentally, again, here's a slide showing all the chlorinated cyanurate chemicals I showed before. But if you actually limit things to what we consider to be drinking water concentrations, only 4 of these are important. So it really simplifies the model for drinking water in that now we only have 6 chemical species we got to model. There's only 6 equations, and only 4 of those are temperature dependent, so that's doable. And so I just want to briefly show you some results of what we've been doing with this. So we did a bunch of experiments where we made various solutions by combining different concentrations of free chlorine and cyanuric acid at various pHs. And we repeated these experiments in a temperature-controlled chamber at every 5 C increment from 5 to 35 C. And so what I'm showing here are the experimentally determined free chlorine concentrations. We're able to use UV absorbance for this because we're working in clean water, plotted against the free chlorine concentration simulated using the O'Brien model, which is only valid for 25 C, just to highlight that if the model was simulating the data perfectly, the points would all fall in this one-to-one line I'm showing here. And that's not the case. And what you see is that the model is overestimating free chlorine concentration as temperature decreases, which just highlights that we just can't use this model at all temperatures, and we need to account for temperature. So we've done that, and so here's again the experimental data, but now shown against using that simplified model I mentioned, and we're actually now accounting for the temperature of the samples, and that's what's shown on this slide. And now we're finding the experimental and model simulated free chlorine concentrations fall very near to a one-to-one line, meaning the model's capturing the real free chlorine concentration in these samples now. And so basically we've got excellent simulation of the data with temperature dependence. So that covers the last point I was actually wanting to make here very briefly, just to make you aware of a web-based application that allows you to simulate the water chemistry of dichlor and trichlor. But again, it's limited to 25C. And this allows you to determine the free chlorine concentration in these systems because it's very difficult to measure right now. But again, it needs to be expanded to cover a range of temperatures typical of drinking water. And that work is ongoing, and that future update to the web application is currently planned. And the final thing I want you to know is in your reference, there's a reference list here of everything I've referenced in here in case you want to learn more about dichlor or trichlor in the future. The other thing I want to do is I want to acknowledge Matt Alexander and Allison Dugan of the Office of Groundwater and Drinking Water, who helped with the experiments that I showed in this presentation. These results were presented at WQTC this last year.
Okay, great. Thank you very much, Dave. For our course, we will then move to our second speaker. But before we do that, if you've missed the poll question and you have more than one person in your room, please go to the question box if you haven't already and type in how many people are in your room. Again, it'll help document how many people are attending the webinar. And with that, we'll move to our second speaker, after which we'll do the question and answer period. So our second speaker is Ying McCauley. Ying is an engineering manager with the Division of Drinking Water in Utah's Department of Environmental Quality. She oversees the engineering review and permitting program of the drinking water facilities in Utah. Ying received a master's degree from the University of Utah. She is a registered professional engineer with 22 years of water-related work experience, and she has worked in various water agencies and utilities. She's currently serving as a trustee of the American Water Works Association Intermountain Section. And with that, I'll pass it on to Ying for her presentation.
Hi, can you guys hear me okay?
Yes, we can.
Okay, how about the screen?
Yep, it's showing up.
Okay, all right. Well, I'm going to talk about Utah's plan review policy regarding the dichlor and trichlor installations. First, I'm going to start with Utah's concerns about using dichlor and trichlor for disinfection of drinking water. We have two major concerns. One is currently there's no EPA approved analytical method for free chlorine residuals in the presence of chlorocyanurates. And because the interference created by dichlor and trichlor chemical. And our second concern is the possibility of overestimation of free chlorine residual due to chlorocyanurates. In Utah, our regulations specifically specify that for primary disinfection, the water systems are required to show that they meet the required disinfection CT, which is the concentration times the contact time. If they use disinfectant for secondary disinfection, they need to show they can maintain the minimum residual, detectable residual in the distribution system, which is C. So by using dichlor and trichlor, we're concerned about if we overestimate the CT and the C, it may lead to the public health risk. So in May of 2016, our staff pointed out the uncertainty related to using dichlor and trichlor and how the chlorine residual reported, whether it's the accurate number. So we started to research this topic, and we contact various experts, including the EPA staff, and we also talked to other states, such as California. So we decided we need to draft a plan review policy to handle the proposed installation of Dichlor and Trichlor. So in August of 2016, we had a kind of internal policy developed, how we're going to handle the proposed facility. And we started to implement this policy when we received new submittals for our review for installing Dichlor and Trichlor. And so at the same time, we also have this policy being reviewed internally by various parts of the various sections within the Utah Division of Drinking Water. So in February 2017, we finalized this policy because we think all the sections within the Division of Drinking Water, we figure out a way to make it work for the division. And this is only Utah policy. We don't mean to, it's a standard for any other entity, but for now, based on what we know of, we are using this policy, and we will continue to work with the existing installations, the Dichlor and Trichlor installations that have been installed before we started this policy. And we first identify the types of the installations in Utah. We have the proposed type, not yet installed. We also have the installation that was installed without our approval. We didn't realize some water systems had switched to Dichlor or Trichlor, or they went ahead and installed Dichlor or Trichlor without our knowledge. And we also have some installations that were previously approved for disinfection before we were made aware of the uncertainty related to the analytical method. And we have some installations, they were approved for other purpose. For example, the water system received approval by stating they are using it for corrosion control. So now our policy, number one, is how do we deal with proposed facility? Our policy is for proposed facility for now, we will not give approval for primary disinfection. If they propose use Dichlor and Trichlor, we will not allow for secondary disinfection either. But if a water system proposes they're going to use Dichlor or Trichlor for other purpose, we said that would be just fine, because many of the Dichlor, Trichlor chemicals, they have received the NCNSF 60 certification. That means it's okay to use for drinking water treatment. However, we will not give primary or secondary disinfection credit to these installations. And the water systems will be required to monitor and report DBPs, and the water system also must submit monthly report of disinfectant residuals for MRDO compliance. And this might be the interesting topic. First, we are saying there's no accurate analytical method to measure Dichlor and Trichlor concentration for disinfection requirement. However, we still need to comply with whether they maintain the minimum residual in the distribution system or whether they exceed the chlorine MCL requirements. So if a facility is approved and installed prior to the implementation of our policy in August of 2016, our policy said the Division of Drinking Water in Utah, we will notify these water systems of our new policy and the associated requirements. The water systems will be required to monitor and report DBPs and disinfectant residuals. However, if a water system detects a confirmed positive E. coli samples when a detectable residual is present, and our level 2 or level 1 assessment finds no obvious cause of contamination, then we're going to say for this installation, we will not accept this water system to use dichlor or trichlor for disinfection, and this water system will be required to switch to a different disinfectant that has that can be measured using an EPA-approved analytical method. Now, during the course of this implementation, while we try to identify all the installation in Utah, we discovered there are several facilities that have been switched over to use dichlor trichlor without the state approval. For these facilities, we notify these water systems, our policy and our requirements. And these water systems, they are assessed significant deficiencies for using on unapproved facilities. And there are several options for these water systems. They can try to obtain the after-the-fact review and approval from us by claiming they are using dichlor trichlor for other purpose, just not for disinfection. Or they can choose to remove the facility or replace the facility, or they can enter into a compliance agreement with the Utah Division of Drinking Water, which would allow them an extension of the time frame so they can find an acceptable option. So in our database, Utah, we use the CITWIS database. We added two the Utah-only indicators, and here's a screenshot of this. We have one that's called CHL2. That's so we can tag a facility in our database, indicating it's for chlorocyanurates for secondary disinfection, or a second indicator, CDCC, means they're just using chlorocyanurates. And here's an example of this water system. You can see we have an indicator showing this water system and this facility is used for secondary disinfection using dichlor or trichlor. So to track these facilities, our process, the first step is we rely on CITWIS database. We add a facility indicator to track each of these facilities, and by tracking in CITWIS, now we can connect each water system's confirmed E. coli positive results with this indicator. And if a confirmed E. coli positive samples are detected, our database will trigger a compliance schedule. And then we can set a time frame for water system to install a facility using approved disinfectant. If the water system can meet the compliance schedule, then they are in compliance and we can update our CITWIS information accordingly. If a water system fails to meet the time frame, we will issue a treatment technique violation. So moving forward, we will continue to track and follow up on the dichlor and trichlor installations in Utah, and we will evaluate our policy based on new information. And we are hoping we can have these informations. For example, we hope that eventually there will be a EPA-approved analytical method for measuring free chlorine in the presence of the dichlor and trichlor, or maybe an EPA policy that is specific to dichlor and trichlor, or EPA publication of the disinfection CT value specific to dichlor and trichlor. Now I'm going to give you a screenshot of this. This is an Excel spreadsheet we used to track the dichlor and trichlor installations in Utah. When we have about 26 cases. And then these are 6 examples. The first case, it's a surface water treatment plant. They use trichlor for disinfection purpose. We sent them a notice in 2017. We require them to replace the facility, and they are currently working on that. The second case is we notify them they meet policy number 4, which means they are allowed to continue to use the existing facility for disinfection purpose, but we will track their performance, and we will take action if they ever detect a positive E. coli or bacteria. The next example is policy number 3, means we allow the facility to stay in service, and we just say you're using it for other purpose, and we don't give you credit for primary or secondary disinfection. And the 2 cases highlighted in yellow are the cases where we found out they installed a switch to Dichlor and Trichlor without state knowledge or approval. So in one case, we did a after the fact review, and we allow them to continue to use it. The other case, the water system voluntarily choose to switch the Dichlor facility with the calcium hypochlorite facility. And the last example is for a proposed facility, and we communicated with this water system. We explained our concerns. So this water system changed the design. So they installed a sodium hypochlorite solution unit instead, and they did not install a trichlor system. So that's Utah's experience.